Hello, welcome to third video of the series on kinematics. In this video, we're going to continue the discussion of motion graph by talking about velocity time graph. So in last video we talked all about the displacement time graph, and over here we'll be dealing with the velocity time graph. Okay, so let me just start with velocity time graph for the simplest motion that we can have. Okay, by the way, the simplest motion, I mean to say no motion. That means I got the x-axis and that's my y-axis. As usual, I'm going to be plotting time on the x-axis and the velocity on the y-axis. Okay, I was telling you about the simplest motion. Well, simplest motion is having no motion at all. Well, okay, that means, I mean to say, like, it's a motion where the body is stationary. If you remember, and if I just take a quick recap, it was my t and it was my d. That's the dt time graph. For the no motion body or the stationary body was this, right, where the position of the body will not change at all. Okay, but in this situation, since no motion means the velocity would be equal to 0 throughout the time, as the time progresses. This is how the line would be like, because velocity is always equal to 0 for a body which is not moving at all. So my VD graph for a stationary body would coincide with the x-axis. That's the time axis. So that was the simplest motion we could have talked about. Alright. Now the another type of velocity time graph is, if you remember, is for the uniform motion where the velocity of the body or the speed of the body will remain same, uniform speed or velocity. So let me just start with the axis. Time goes on the x-axis and velocity goes on the y-axis. Let me just put y there. And it's okay, I mean, right at the start of the case, if I say that, okay, if the body is moving with a constant velocity of 5 meters per second. Now, I need to be sure about the unit, that's meter per second. So if it is moving with the uniform speed, at every point of time, you'll figure out that the speed of the object remains the same. That means at 1 second, you're going to find out it's 5 meters per second. And as time progresses ahead, there is no change in the value of velocity. That means if I want to draw the graph for a velocity type graph for a body which is moving with the uniform speed, graph would come out to be a straight line parallel to the time axis. Now in contrast, if I try to remember the dt graph for uniform speed motion, let me just see. That's my time axis, that's my d-axis, and there it was. It was a line, a straight line inclined with the time axis. So that's the contrast between VD graph of a uniform speed, a body which is traveling with a uniform speed, and the DD graph of the same. Okay, now it's the important stuff. The important thing is that now the body would be accelerated. Okay, so velocity time graph for an accelerated body. So as I told you, uniform acceleration means the velocity of the body would increase by the equal amount at regular interval of time. So let me just start with putting the time on the x-axis and the velocity values on the y-axis. 1, 2, 3, 4 meter per second. That tells you that I'm plotting v on the y-axis, and that's 1, 2, 3, 4, 5 seconds, and that's time on the x-axis. Yeah. So the case right now in my hand is a body which is uniformly accelerated, and I've been repeating this so many times, that uniform acceleration means there will be equal change in the velocity value after each regular interval of time. So after 1 second, I would say that if the velocity increases from 0 to 1 meter per second, and after 2 seconds it increases to 2 meter per second, so there is equal change in the value of velocity. At the end of 3 seconds, as you can imagine, it would come out to be 3 meter per second, and so on and so forth. Okay, and if I join them, it turns out to be a straight line inclined to the x-axis. And if I just remind you of the dt graph of an accelerated motion, it looked something like this. That's my time, that's distance, and it used to curve upwards. Fine. And if I just take the liberty to draw the deceleration, now let's see what deceleration actually shows you. For a deceleration to happen, it should start from some initial velocity, right? I mean, deceleration is nothing but decreasing the speed. So that means initially the body was traveling at some higher speed, and after 1 second there is a loss of or decrease of 1 meter per second in the speed. At the end of 2 seconds, it is another decrease of 1 meter per second. So now from 4 it has been dropped to 2. At 3 it would be 1, and 4, as you can imagine, it would drop down to 0. So for a uniformly decelerated body, this is how the graph would come out to be. That's uniformly decelerated. That means velocity of the body is decreasing equally at the regular interval of time. Let me just put this thing. And well, this graph is for uniformly accelerated motion. And if you remember, if I want to draw this graph, that is the VD graph for uniformly decelerated motion, and if I want to draw the counterpart on the DD graph, it looks something like it starts with a greater velocity, it curves down and becomes stationary. As you can see that the final velocity, the eventual velocity of the deceleration will be equal to 0. So my DD graph will become parallel to the time axis. Okay, in another type of VD graph where we will think about a situation where I would say that the acceleration is of course the acceleration, but the acceleration is not same or uniform like previously we had. So let me just see how it looks like. That's a VD graph, and now it's, I would say, like, okay, it's increasing acceleration, which actually has no scope here in this one. I mean, you know, at this particular level, just for the knowledge purpose, I would try to give you the idea. That's my time axis. Now that's my velocity axis, and as it says that it's increasing acceleration, so every time the change or the increase in the velocity would be more. So it starts from a lower velocity and it goes on increasing non-linearly, I would say not equally, and it turns out that the shape of the graph is an upward curve where the velocity increases on and on with increasing acceleration. It's not regular, it's not a straight line, so you can say that it's not a linear, it's not changing linearly, right? As I told you, we're going to be having no use pertaining to this particular syllabus that we are referring to. So moving on to how to analyze the VD graph. In questions, you'll be given a VD graph, and I briefly explained you earlier in the earlier video that we can calculate from the velocity time graph the distance or the displacement. We can calculate distance, displacement, and the velocity, which is not a big deal, and we can also calculate the acceleration. I will actually take a bit of time to explain everything to you in this particular video, how to analyze, because that happens to be a very important part of this video. That's the analysis of VD graph. Okay, so let's see. that is analysis of a VD graph. I mean, it's not a very difficult thing. I mean, I use the analysis word. Analysis is just how to figure out, how to calculate the stuffs from VD graph. Like if suppose I have a VD graph, let me just give you a very simple example at first. I got this this VD graph where where the line is something like this. Okay, now it seems like the VD graph is a straight line. Obviously, I can say that the body is under uniform acceleration, right? Because it's a straight line and it happens to be making some sort of angle with the time axis. So my body is uniformly accelerated. Okay, now as I told you, I can calculate the distance from the VD graph. I can calculate the distance from the VD graph. Let me just tell you how can we calculate it. Calculating the distance is easy by calculating the area under the curve, area under the line. That means if suppose someone tells you like, okay, find out what is the distance traveled by some object which follows this particular VD graph by time x, some time x. Okay, so that means I need to find out what is the distance traveled by the object during this particular time. As I told you earlier, the distance can be calculated by calculating or measuring or maybe finding out the area under the curve. So if this is my line, I mean of course this is my line, which happens to be, okay, in other terms I can call this a graph. Otherwise it can be misleading, of course. So if this is my graph and that's my limit, I need to figure out the distance traveled under this particular time. I will be interested in calculating the area of this triangle. And yes, once I calculate this, that will give me the distance traveled by the body. Okay, that's one thing that we can calculate from VD graph. Now there is acceleration. I am just staggering the discussion of velocity for a while. Acceleration. Acceleration can be calculated from the VD graph if we are able to calculate the gradient of the line. So if someone say that, okay, what is the acceleration in this situation, and I'll be calculating the gradient of this particular line, the blue line, by taking the same, okay, considering this, okay, there are 2 points on the line. What is the rise between that line and what is the run of that line? So it's more like calculating the gradient of the graph can give you acceleration. It's just an idea for the timing. We'll also discuss everything with an example as well. Okay, so the last part I would say is the velocity. And it's not a big deal. When you can read off everything from the VD graph, it's not difficult to read out, okay, if suppose someone asks you what is the velocity at time x, well, of course this is what it is. You extrapolate it on this y-axis. It's like kind of find out, okay, consider this point on the line. You already have seen the x coordinate. Find out what's the y value, and y value happens to be the velocity. That's your answer. So it's as easy as that. What is important is to remember that we can calculate the distance from VD graph by calculating area under the curve of the graph, and we can calculate the acceleration by calculating the gradient of the given line. Alright, so there is an example over here of speed time graph, and we'll see how can we deal with. There are a lot of stuff that we need to calculate, as we discussed earlier. Well, first of all, we will try to calculate what the distance is. Distances. We'll also be talking about what is the acceleration. But before that, it's very important to understand what the graph says to you. What exactly the motion of the body is, whether it's accelerating, it's stationary, it's moving with a constant velocity or something. So it's very important to understand the graph first of all. So I can see there are 3 straight lines, and accordingly I'm going to be dividing them into three different parts. So there are three different parts I get. From time from 0 to 20 seconds, it seems like the speed time graph goes up. That means it's a straight line. So I would say that it's an accelerated motion, right? There is an acceleration out here. Well, that's because it's a slanted line. From 20 to 50 seconds, I see that it's the horizontal line. So if you remember, since it's a VD graph and the graph is parallel to the x-axis or the time axis, the speed remains the same. As you can see, 20, it remains same from here to here. Okay, and after that, from 50 to 60 seconds, well, it drops down to 0 again. That means somehow the speed is decreasing from 20 to 0. That means there is a deceleration area. So let me just write down area 1, or stage 1 rather. That sounds nice. Stage 2, stage 3. Okay, stage 1, as I told you, is uniform acceleration. So it's very important, very important to identify what's given in the graph. The second stage is well, uniform speed, or same speed I would say. We can also say velocity, because we're not talking about the direction right now. And the third thing that I got from here is that there is a uniform deceleration. How can I say uniform? Because it's again a straight line. That means from here, from this end to this end, the velocity, the value of deceleration would be same. So that's uniform deceleration. Fine, I understood. I know everything about the graph right now, so there is no big deal. There shouldn't be any difficulty. If I start from acceleration, because that happens to be the easiest thing that I can do first. So well, let's start with calculating gradient here. Gradient, that means I'm calculating the acceleration. So acceleration at the first stage would be equal to the gradient of at the first stage. And as I told you, gradient can be calculated as rise, that's from 0 to 20. So the rise is from 0 to 20, and then run, that's from 0 to 20 again. So it's like rise is on the y-axis and run on the x-axis, 20 over 20, and that gives me 1, I think, 1 meter per second square. That's the important thing, the unit of the acceleration. Well, continuing the streak, I can also calculate what's the acceleration at the second stage. So acceleration at the second stage would be again the same thing. The gradient of that line of wait, let me just correct it. There should be 3. So that's 3 here and 3 here. The rise now is from 20 to 0. That means it's actually kind of negative. So negative 20. Why negative? Because it is decreasing right now, and acceleration is always a vector quantity. So if I talk about the acceleration, it has to be a number plus the direction. Direction, because the velocity is decreasing. It has to give the idea that okay, this is in fact a deceleration, right? You know, acceleration is negative. That gives that is nothing but deceleration. Negative acceleration is deceleration. So let me just make it more clear. Negative acceleration is nothing but a deceleration. Okay, that's an important thing. And there is another name for deceleration. Sometimes we refer to it as retardation as well. So we are actually kind of retarding the motion of the body. That's what it is. Okay, let's go back to the situation where we were calculating the acceleration in the third stage. So we wrote about the rise, that comes out to be negative 20, and the run is from 50 to 60, that's 10. That's negative 2 meter per second square. So if you compare them, the acceleration of the body is lesser than the deceleration. That's why the body takes a greater time to accelerate up to 20 than time taken by the body to decelerate. It accelerates from 0 to 20 in 20 seconds. So why? Because acceleration is smaller. Deceleration is more. That's why it drops to 0 suddenly in a matter of 10 seconds only. So yeah, acceleration can be calculated using the gradients, as you can get the idea from here. Okay, the next part that we'll be talking about is the distance. Distance traveled in, say, entire journey from 0 to 60 seconds. That means if I need to calculate, if I want to calculate what is the distance, and if you remember, I told you we can calculate the distance by calculating, or like finding out what is the area under the graph. Okay, so let me just clear out those like those markings on the areas. Yeah, that seems fresh now. Okay, so let's get started. As I told you, in order to calculate the distance, what I need to calculate is the area which falls below this, below the graph that I already have. That means the shaded portion over here from this end to the other end. Okay, so if you look at the shape of this particular stuff, there are different ways to do it. There are like complicated ways to find out the area, and the easiest way to find out the area. So you can calculate the area by dividing into three pieces, like one triangle, one rectangle, another triangle, and that's a long cut, I'd say. Okay, so if you look at the shape of this area, it looks more like a trapezium. So in this situation, it's very important to remember the area of trapezium. The formula for area of trapezium, if I say it's half multiplied with sum of parallel lines. So sum of parallel lines, that means I need to add this line, and before that I need to figure out what that is. And 50 minus 20, that is 30, and this is obviously 60. So 60 plus 30 into the height, and height's like from this end to the other end, that's 20. That turns out to be 90 times 10. That's what my calculator says, and that is 900. And be careful about the unit, it says meters. So yes, that is the distance traveled by the vehicle or the car from 0 to 60 seconds, and that comes out to be 900 meters. So yeah, this because of all this, I say that VD graph, the speed time graph, is always important thing, because it gives you a lot of stuff. It gives you a lot of knowledge about what's going on there in the motion. Okay, so while continuing the streak, I'll again solve an example, maybe a little bit tedious one, but yeah, that will gonna make the entire thing even more clear. Okay, all right, this one, yeah, this was I was talking about. Again, as I told you before, I can start the calculation. It's very important to write down the description of this thing. So from A to B, okay, there's something happening there. Okay, from A to B, it's very easy to divide the entire equation into different parts. From A to B, it seems like it is a constant line up there. So it's uniform acceleration. Uniform acceleration. From B to C, let me just divide this. That's the second part of my problem, BC, and it's flat. It's parallel to the time axis. It's moving with the uniform speed. Well, I was just about to say like it was stationary, but then alright, this is not a DD graph. This is the VD graph, where parallel lines means uniform speed. Okay, and then there is another part which says the part CD. Okay, part CD. Alright. Part CD. You can see that there is a drop in the value of velocity, so it seems like it's a uniform deceleration. I will not be even giving it a second thought. And then finally, D to E is, check it out. There seems to be something here, right? It's again, the value is dropping from D to E, the velocity. So again, I would say that this is uniform deceleration. Well, let me just make it more clear, otherwise it's pretty confusing. That's a uniform deceleration. Alright, you must be having a huge question. What's the difference between, what exactly is the difference between C and D and E? I mean, if they both denote the value of, they both denote deceleration in the vehicle. Okay, if you look closely, there is difference between the gradient. So what would be the basic difference? Okay, so as I told you, there's a difference between the gradient values over here from C to D and D to E. So possibly the deceleration value would be different for both of them. This is more inclined. There will be the value of deceleration would be more here as compared to this, because the angle that it makes with the time axis is less. While if you compare the horizontal line and compare the angle over here, it is more. That means the gradient value for this is more than this, and therefore the deceleration here would be more than this. Okay, and if you look at the things carefully, it turns out to be exactly the same thing. From A to B, the value of acceleration can be calculated using the rise over run. So, well, acceleration from A to B, that happens to be from 24A, that is 16 over, that's run, that's 4, and that's my 4 meter per second square, because acceleration, right? Okay, and if you look at the CD, acceleration of CD, that happens to be negative, right? Because I'm writing acceleration, not deceleration. So I'll calculate what is rise. Rise is from 12 to 24. That happens to be 12. 12 to 24 is yes, of course, it's 12. And then the run is from 8 to 12. That happens to be 4. So 3 meter per second square, and I shouldn't be forgetting that negative sign, because it's nothing but the deceleration, negative of acceleration. And let me just calculate the deceleration of my CD part. Acceleration, let me just call it acceleration of DE part, and since it should be negative, it's falling down. The rise is from 0 to 12, or rather 12 to 0, that's negative 12, divided by, it's like 12 to 18, and 12 to 18, if I remember, is 6. Yeah, of course it's 6, and well, it comes out to be, well, negative 2 meter per second square. Now, as I told you earlier, you got to compare this value with this one. If you look at the magnitude, only the number, as I told you, the number of this cell, I mean the gradient of this graph, this part of the graph, would be greater than the number of the acceleration, or the gradient of this graph would be, okay, I mean, you know what, the gradient here would be higher than the gradient here. Okay, so yeah, this can be helpful in calculating the acceleration of the body at various stages. Now let's talk about the calculation of distance. Okay, there are different parts, and this is more complex actually. So we're gonna actually have to consider them in parts. So let me just calculate this part. The area over here. I think I need a little bit space over here. Let me just clear them out. Okay, I got some more space over here. So let's get started. So distance traveled in part AB would be equal to trapezium. The formula for area of trapezium is sum of parallel lines. That's 8 plus 24. 8 plus 24 times the height of them. That's the height of the trapezium. That's 4. And the value turns out to be not as easy as what I thought. So the value of this would be 32. And that's 64, and let me just check the unit. That's meter per second. So that's the unit, meter per second. Wait, that happens to be the velocity unit, right? But here we are calculating distance, so possibly I will be writing just as meters, because I am calculating here the distance. Okay, now, well, part BC, that sounds no difficult because it's just a simple rectangle piece. So, well, rectangle is length into breadth, I suppose. So that's what it is. Distance traveled in the BC part distance traveled in BC part, that is the length multiplied by the breadth. So that's length 24, and the breadth is 8 minus 4, that's 4, and 4 times 24 is 96, I think. Okay, yeah, 96 it is. And that is meters. Okay, now here again, let's check it out. I need to calculate this part of the distance, that means distance in part CD. It looks more like a trapezium, I think. So half into sum of parallel lines. One parallel line is 12 meters long, and it should be sum, rather. That's sum sign, it's positive sign. Let me just correct it. Yeah, that should be sum. And the other parallel line is 24 there. It's 24, and the distance, so the height of the trapezium is 4. So it turns out 36 times 2, and that comes out to be 72 meters. Let me just recorrect my, let me just recheck my mathematics. Okay, that's 12 plus 24, it comes out 26 times 2, that's fine. Okay, that's 72 meters. Fine. Oh, I think I need more space to calculate the other distance. So let me just make more space. Oh, poor acceleration guy. I mean, it went out for nothing, right? Anyways, the last part of the thing is the DE, the area at DE. The distance covered at the area DE would be equal to, and since it's, I mean, a very simple thing, it's the area of a triangle, that's height is 12 times the base, it's 18 minus 12, that is 6, that comes out to be 36 meters. Alright, we haven't done anything. I mean, for the till this time we haven't done anything. I mean, I need to calculate the total area, right? So in order to get the total area, I need to add up all the areas. And why am I calculating the total area? Because I need to calculate what is the total distance traveled by the fellow. So it's like from this end to the other end. The area would be sum of all the numbers that we just found out. So that's like 64 plus 96 plus 72 plus 36. So the total distance would be equal to 64 plus 96 plus 72 plus 36. Okay, my calculator says it is 268. Well, a very odd number though, but we can't say because that's what our things are getting at, right? So, well, that's 268 is the distance, that's 6 by the way. 268 meter is the distance traveled by the vehicle, and this is what it is. So, this is why analysis of VD graph is very, very important. I hope that you solve more of the examples related to VD graph and make yourself more comfortable with how to define, describe, and analyze the motion of a body that you can read out from the VD graph. For the time being, we're going to stop here. Thank you.